Good morning. This is Dr. Prescott. I want to warn you ahead of time that I am doing these lecture recordings mostly from my home, so you may hear a dog bark or a chicken crow, so just giving you a heads up that that may happen. I also have not recorded these without an audience before, so hopefully these are still helpful for you. My approach in doing these lectures is to point out points of confusion that I've known for students to have in the past and to try to give you some tips on those. I will not attempt to go through every piece of the chapter in the text. It is expected that you will read each chapter and be familiar with the concepts. There will be some that we will not go over, and when that's the case, I'll specifically let you know that you're not responsible for that material. But otherwise, assume that what is in the text is something that you could be asked on a quiz or, well, actually on your homeworks or on exams in the course. I'll give you more information about the course when we meet online through Schoology, but feel free to ask questions then if you have questions on the course itself. So let's start with Chapter 0. This is a little odd that they've started with a 0 chapter, but this is basically a very overview chapter of things that you should have learned in a high school chemistry course. So I'm going to point out a few of them and point you to some practice problems if you are either out of practice on this material or this is something you haven't looked at in a long time. But mostly this chapter is just really some fundamentals that you need to know in order to be successful in future chapters of the course. So do make sure that you're comfortable with all of the material. Okay, so right on cue. So let me pick up from where we left off. So starting with this chapter, the first things that are in the chapter are on measurements, units of measurements, and the types of units that we use. So you can see here the list of the 7 fundamental SI units of measure that we typically use to measure different types of physical quantities. You should be familiar with these and their abbreviations. Here you see some prefixes for how we determine either multiples of units or portions of a unit, say a centiliter or a milliliter, what those mean mathematically. You should be able to convert from any one of these to the other, or from any one of these to the main unit. So say, for instance, a decimeter to a meter, or centiliter to a liter. That's what I mean by the main unit. And in order to do that, you just use what the prefixes mean in order to convert from one to the other. For example, there are 1,000 milliliters in 1 liter, and you can use that conversion factor to convert any amount of milliliters that you're given into liters. We'll see in a little while a way to do that. It's called dimensional analysis or unit analysis, and it's a great way in chemistry to set up all of the types of problems that you're doing and in a systematic way be able to solve them and always be able to solve them accurately. So again, you should be familiar with these prefixes that you see here. These are just some general definitions of some of the units that we use to measure mass, and obviously balances that we use in the laboratory to measure that mass. A little history on what the meter means. Another type of measurement is measuring temperature. This should say temperature at the top here. One thing that you should be able to do is to convert from Fahrenheit to Celsius to Kelvin and vice versa. So between any of those 3 types of measurements. And you can see here the formulas to use to be able to do that. A note on formulas: you are allowed on your midterm and final exams to bring a sheet of paper with anything written on them. So if there are any formulas like these that you see here that you need for the exam, it's your responsibility to make sure that those will be on the sheet that you bring in. I do not provide a sheet of formulas for you because you do have that sheet that you can bring into the exam. So here you can see how you would convert from Fahrenheit to Celsius or from Kelvin to Celsius, and the ways to go about doing that. We also have what are called derived units. These are units where we take standard units and combine them. And so in that sense, they're derived. Most of these I'm sure you're familiar with. The volume is area times length, density is mass per unit volume, etc. And then on the right, you can see the units that are used for them. The units correspond to the type of quantity you're looking at. So for example, area is length times length. So length is measured in meters, so when you multiply the two, you get meters squared. So that's where the derived unit comes from. Likewise, if you look at, say, speed is distance per unit time. We measure distance in meters and time in seconds. So you can see the unit derived there is meters per second. So the derived units match up with the actual definition of the quantity that you're measuring. This shows just some of the conversions between cubic meters, cubic centimeters, and decimeters, and their volumes in liters and milliliters. The one to pay most attention to is that 1 cubic centimeter is equal to 1 milliliter. The most common types of conversions that I'll ask you to do are from cubic centimeters to milliliters, and then they're from liters. So obviously a milliliter is 0.001 of a liter, so that would be the conversion there. These are just showing some instruments that you'll see in the lab that you can use to measure volume. Density is derived unit. It is mass per unit volume. The mass is usually described in units of grams. The volume either in milliliters or cubic centimeters most often. And you can see up above there's a table there with some densities of some common substances. You will need to be able to calculate density given mass and volume, and or calculate mass or volume given the other two. So basically, just given two of the unknowns, giving two knowns, solve for the unknown amount. Energy, this is just a very brief introduction here. The SI unit for energy is the joule. It's equal to 1 kilogram meters squared per second squared. You'll also see us use, when we talk about that later, other units of the calorie or the kilocalorie, and those are just some of the conversion factors you can use to convert, say, from calories to joules. Another piece of information that's important for just general performance in the lab and just in terms of what we'll talk about are ideas of accuracy and precision, and then how that relates to significant figures. Most students come in thinking that significant figures are just this random thing that you do with numbers, and sometimes you round them and sometimes you don't. It actually applies to how we make measurements in a laboratory. So the significance of significant figures tells us about that measurement that we're making. So first, the difference here between accuracy and precision. So accuracy is how close to the true value a given measurement is. Precision is how well a number of independent measurements agree with each other. So if you made, say, 5 different measurements, how close they were to each other would be a measure of their precision. How close they were to the true value would be a measure of their accuracy. So here's just an example. This is showing a mass of a tennis ball using 3 different types of ways to get that mass: a bathroom scale, a lab balance, and an analytical balance. And what you can see is that there are different numbers of significant figures in each. There are 2 significant figures that the bathroom scale can report to. There are 3 significant figures the lab balance can record to, and the analytical balance can record to 6 significant figures. So the number of figures tells you a bit about that measurement and about the instrument that you're measuring with. So if you look at the bathroom scale, you can see that there's poor accuracy and poor precision. Obviously, the mass of the tennis ball is somewhere around 54 grams if you look. So none of those measurements are close to that, nor do they agree with each other. You see a 0.1, a 0, and a 0.1, so there's poor precision there. If you look at the lab balance, you can see that there's fairly good accuracy, given that the tennis ball is assuming it's 54.4 grams or something around that. There's fairly good accuracy. Each of those measurements comes close to that value. However, if you look at the three, there is poor precision over them. You have a variance of that 54.4 to 0.5 to 0.3. And then if you look last at the analytical balance, you can see obviously very good accuracy and good precision. You see that a lot of those numbers are the same for each of the measurements that are made. And so we would say that that has both good accuracy and good precision. Okay, so a little bit about significant figures. As I mentioned before, they are used in measurement. They do give us an indication of how precise and accurate a measurement is. They are the total number of digits that we record for a measurement or a calculated quantity. Okay, try that again. So significant figures, these are the total number of digits that we record for a measurement or calculated quantity. All digits but the last are certain, meaning we know for certain that that is an accurate value. The last digit is an estimate. So when we measure something, we record the number of figures plus one last one that is an estimate. And you'll see in a moment an example of that. Exact numbers, so these are numbers that come from, say, dollar amount. So, something's $23.65. That's an exact number. They effectively have an infinite number of significant figures. But let's take a look at in terms of measurement. So if we look here at this ruler, you can see that the ruler measures in centimeters, and that black bar at the top is goes to that 1.7 centimeters, but a little bit beyond it. And so that little bit beyond would be the next digit that we're going to estimate. So when we measure with any type of instrument, we always include that extra digit that is an estimated value. So if you look here, we would estimate the length here at 1.74 centimeters. Now, even though that number is an estimated value, it is considered a significant digit. This is often a point of confusion for students. So for every type of measurement we make, we always estimate a value one beyond the ability of the instrument. So if you see here, obviously there's no marking for that 4 in the 1.74. We're estimating that value. And that is how you make all measurements in the lab. You estimate one value beyond the ability of the instrument. And that value is considered to be a significant figure. So in the length of 1.74 centimeters, that contains 3 significant figures. So here are our rules for counting significant figures. And the rule follows with an example for you. So zeros in the middle of a number are like any other digit. They're always significant. So 4.803 centimeters contains 4 significant figures. Zeros at the beginning of a number are not significant. They only act to locate the decimal point. They're sometimes known as placeholders. So if you look at this point 00661, that contains only 3 significant figures, the 6, the 6, and the 1. One way to help you decide how many significant figures you have is to take any number like this and express it in scientific notation. When you do that, it forces you to see only the significant figures in the value. So that's one tip I give students if you're struggling with that particular aspect, is to take the number and express it as a scientific in scientific notation, which, yes, is a skill you need to be able to have as well. And then you'll see that it really has just those 3 significant figures. Zeros at the end of a number and after the decimal point are always significant. So you can see here 55.220 has 5 significant figures. Because again, if we were measuring this is Kelvin, so if we're measuring this on a thermometer, we'd be estimating that 0 value. It is still considered a significant figure. Zeros at the end of a number and after the decimal point may or may not be significant. And here's an example. So 34,200 meters. Notice that there is no decimal point there. And so we're not able to determine whether those zeros are significant or not. If you think about when you would express this as in scientific notation, you could express it as 3.42 times 10 to the 4. So you would need more information to determine that. Okay, so those are our rules on deciding how many significant figures we have. Oftentimes, you need to be able to keep track of significant figures and figure out how many significant figures to have in your answer. Okay, so you are performing some calculation, you have one number that has 3 significant figures, another one that has 4, as the example here, and you need to figure out how many significant figures to report your answer to. So here are the rules for doing that. If you are multiplying or dividing numbers, then your answer can't have more significant figures than either of the original numbers, or any of the original numbers if you have more than 2. So if you're doing a calculation that involves multiplication or division, you want to look and find out the number of significant figures of all your values, figure out the lowest one that you have, and that's what you can report your answer to. So if you notice here, you've got 3 significant figures in the 278, 4 in the 11.70, so you can only report your answer to 3 significant figures to the 23.8. Rules for addition or subtraction is that the answer can't have more digits to the right of the decimal point than either of the original numbers, or any of the original numbers. If there's more than 2, this follows for that as well. So you look at all of the values that you have, you look to the right of the decimal point, and you determine how many significant figures you have there. Determine how many digits you have to the right of the decimal. So if you look 3.18, there's 2 to the right of the decimal. In 0.01315, there's 5. The lesser of that is 2, so you report your answer with 2 digits to the right of the decimal. This is different than multiplication or division. You're focusing on how many digits are to the right of the decimal place, and then using that rule to figure out how many digits to the right of the decimal in your answer. Often when you are doing these types of calculations, so in the previous examples here, you might end up with not 23.8, but 23.74, or whatever this answer might be. So you have to figure out, how do I round it to get it to 3 significant figures? So here are the rules for that. So if the first digit you remove is less than 5, you round down by dropping it in all the following digits. So if you're looking at a number here that says 5.654525, and you know your answer has to be to 3 significant digits, then you are looking immediately to the right of that 3, so looking to the 4 that's there. It's less than 5, and so you drop it in all of the following digits, leaving you the 5.65. The other way to think about this is, if that digit is less than 5, you essentially leave it alone, and it becomes 5.65 as it was before. I find that an easier way to sort of think about that. If that first digit, however, is 5 or greater, then you round up. So in this example, 5.654525, I need my answer to 2 significant figures, and so I'm looking at that 5. It is a 5, so I'm going to round that number up to make it 5.7. So you're actually rounding the 6 up to 7. So again, what you're looking at here is, of those significant figures I need to report, I look 1 digit to the right of the last one, and use that to determine whether I'm leaving the digit alone or rounding it up. Those are your options. And then the last here, if the first digit you remove is 5 and there are more non-digits following, you round up as well. So I think I misspoke here. I think number 2 is if it's 6 or greater, you round up by adding 1. If it's 5, then you look next to that to see whether you round up. Okay, the last sort of main piece here for this chapter, in terms of preparing you for calculations in the course, is how you convert measurements from one another. This is also the way that I'll have you calculate a lot of the types of problems that we'll be dealing with. I'll have you set them up in similar ways, using what they call here dimensional analysis. It can also be called unit analysis, where you're actually looking at what are the relationships that you have, and then using those to convert from one to the other. So you take an original quantity and you multiply by a conversion factor, and you get that equivalent quantity that you're looking for. So let's see if there's another. Okay. So they're giving you a relationship here of 1 meter equals 39.37 inches. You could use that in the two ways that you see here, where 1 meter is on the top and 39.37 inches is on the bottom, or you could use 39.37 inches on the top and 1 meter on the bottom. The most common error that students make is putting something on the top when it should have been on the bottom, or vice versa. So the way you do this is actually to look at the units and work to cancel out the units so that you end up getting the unit you want in your answer. And I'll show you how that works. First, let's look at an incorrect method. So we started here. So the question here would have been, convert 69.5 inches to meters. Okay, so let's assume that was the question. And you can see here that the way they've set this up, you've got inches on the top in 69.5. You've got inches on the top in 39.37. Inches times inches gives you inches squared. That is not what you want for your answer, right? You're looking for meters in your answer. You already know that something's wrong here. So let's think about setting this up in a different way. So here we set it up where the conversion factor has the meter on the top and the inches on the bottom. Notice that the 69.5 inches on the top cancels with the inches on the bottom in your conversion factor and leaves you with meters on the top in your answer. And that's what you're looking for, is meters in your answer. You were given inches, asked to compute to meters. If you always do it this way, if you always include these units and cancel them out and check to make sure that the unit you end up with is what you're looking for, it will be a great way to make sure that you're setting these problems up accurately. This goes for any type of conversion. So when we start talking about grams to moles, or number of atoms, number of molecules, when we talk about energy, converting joules, all of these types of problems, if you use this method, will help you immensely in getting the right answer. So in terms of the calculation here, we just take the 69.5, divide it by 39.37, and get the 1.77. Notice that we have 3 significant figures in 69.5, 4 in 39.37. The 1 meter is an exact number, so it has an infinite number of significant figures. So our lowest number of sig figs here is 3, so we report our answer to 1.77 to 3 significant figures. Okay, that's essentially it for the main types of calculations that you need to be able to do for this chapter. I would suggest, and I would make the suggestion for any of the chapters, that as you're reading through them, you look at the problems that are within the text and make sure that you can answer all of them. So how the text works is it's broken up into sections. After each major section, they'll have a couple of questions. They may have a worked example for you to see, and then follow-up problems after that. You want to make sure that you can both follow the worked problem and then also do the problems that are following it. If you're not able to successfully do those problems following it, then you should go back and review that section again until you can be successful in solving those problems.